Good day, guys. I hope you guys are good. Today, as we will continue with AC machines, the last time I just introduced it to you how does AC calculations work, especially pertaining when we are dealing with three-phase systems. We said when we're doing three-phase system, given values are always the line, and when we're doing calculations, we use phase values to do the calculations. And now we are going to talk about the first part of our calculations in this topic of AC machine. We'll be looking at the EMF equation of synchronous alternators. Okay, we'll be looking at the EMF equation of synchronous alternators. Firstly, just to introduce the topic, what is an alternator? An alternator is basically a generator, but it is a form of a generator that produces alternating current. That is why it is called an alternator. Okay, remember, according to Faraday's law, in order for us to generate EMF, basically in order for us to generate electricity, we need a magnetic field. Okay, I'm not gonna write it, I'm not gonna spell it all because I'm trying to be within time. Okay, we need a magnetic field, and also we need a conductor, which we normally, in most cases, a conductor, we normally call a coil. Okay, then there must be a relative movement, relative movement or motion. There must be a relative motion between the magnetic field and the conductor in order for us to produce an EMF. Okay, what does that mean, guys? It means it's either the conductor will move with respect to the magnetic field, or the magnetic field will be the one moving with respect to the conductor or coil. Then we generate EMF. Okay, let me just show you a simple thing of what we're talking about here. Here is a magnetic field, a north and a south. Okay, then here is the conductor. Sorry, yes, let me use a dot circle method to represent the conductor. Here is the conductor. This is the conductor, cylindrical. Okay, we know a magnetic field, a magnet has a magnetic field around it. Okay, so according to Faraday's law, if we have a magnetic field and a conductor, which in most cases we call a coil, and there is relative motion between the two, it's either we are moving the conductor through the magnetic field, or we are moving the magnetic field cutting the conductor. We will generate EMF. That is how any generator operates. That is how any generator, whether it's a DC generator or an AC generator, but in this case we are talking about synchronous alternators. So, but this is the working principle of any generator, guys. Now let us talk about the construction of synchronous alternator, or basically the construction of AC machines. AC machines have two main parts. Okay, remember, a generator and a motor have the same construction. That is why I'm saying the construction of AC machines here. That is why I'm saying the construction of AC machine. They have two main parts, which is the rotor and the stator. Okay, the rotor is the rotating part of the machine. The stator is the stationary part. Okay, because we're talking about alternators here, I'll just briefly explain the construction of these synchronous alternators. Okay, so let's say this is my stator. Okay, I'm not a good drawer, but this is my stator. Okay, the stator has slots within it in which we wind the stator coils. So, stator coils. Okay, these are the stator coils. Then there's the rotating part. This is the stationary part. Most we said it's a stator. Then there's a rotating part, which is the rotor. Okay, the rotor, it depends on which type of rotor, because there are different types of rotors. There's a squirrel cage, and there's also a wood rotor. So in this case, I'm just referring to the wood rotor, hence I'm gonna draw rotor coils. These are rotor coils. As I've briefly explained, in order to generate EMF, there must be a what? A conductor, magnetic field, and relative motion. Okay, in large alternators that are used to generate electricity in ESCOM power stations, in large synchronous alternators, the one that is moving is the magnetic field. The magnetic field is in motion with respect to the conductor. So the magnetic field is the one that is in what? In motion. This will eliminate the uses of brushes. That is why they do it that way. Okay, so that means in this construction, the magnetic field is produced, the magnetic field is the one that is attached to the stator, is the one that is what? Rotating. The magnetic field is the one that is rotating. I wanted to say attached to the rotor. The magnetic field is attached to the rotor, so it is the one that is rotating. As the rotor is rotating, and it has a magnetic field, and this magnetic field will cut the stator conductors, these stator conductors. Then that is how the EMF is produced in synchronous alternators. Okay, but now let us get to the most important part, this EMF equation. This was just, you don't have to worry much about it. This was just to give you a general idea of a synchronous alternators. This was just to give you guys a general idea of synchronous alternators. Okay, how does this equation go? Let us write down the equation first, then I'll explain each quantity that is in the equation. I won't derive anything other than I'll just write the equation down, and how do we apply the equation in solving calculation problems. Okay, the EMF equation goes as follows. Okay. Okay, the EMF equation goes as follows, guys. In most cases, guys, because we'll be mostly the calculations that we'll be doing. I rarely see a calculation that talks about a single phase in this topic, but in most cases we are dealing with what? 3 phase. We are dealing with 3 phase. And I said with 3 phase, given values are all in line values, and when you are doing, or before you use any value in any equation, you must convert it into a phase value. So this EMF is this EMF, guys, is a phase value. It's the phase EMF of a 3-phase alternator. You can use the same equation for the what? For the single phase. Okay, just that in single phase you don't worry about line and phase values. So this is the phase value of the what? Of the EMF. This is the phase value of the EMF. Okay. This is the phase value of the EMF. Then this one is the frequency. This is a frequency, yeah, and I'll show you how we calculate, because there is a formula that we normally use to calculate the frequency, because it is not always given in the question. Then this is the useful flux, yeah, and it is in what? In webers. Then this is the turns per phase. Turns per phase. That is why we say TP is turns per phase. Then this is the form factor, KF. Then this is the pitch factor, and this is the distribution factor. Okay, so what is important? It's a straightforward equation, but you must be able to understand this equation and to apply this equation. Otherwise, you'll never be able to solve calculations pertaining to this topic if you don't know how to use or apply this equation. Okay, firstly, I'm going to talk about the frequency. Normally, when we want to find the frequency, we use the formula for the synchronous speed. We use the formula for the synchronous speed. You will be given the synchronous speed of the, and guys, the speed that is given in synchronous alternators is only the synchronous speed. Okay, remember it is called synchronous alternator, meaning the rotor and the stator magnetic field are equal. The rotor and stator magnetic field are equal. So we normally use this formula to find the frequency, where the question will give you the speed and they will tell you the poles, the total number of poles. This is a synchronous speed. We want to find this. Then this is the pole pair. Let's say if the question is saying to us an 8-pole alternator, that means the pair is what? Equals to 4, since it is an 8-pole. Okay. Then you use this to find the frequency. We don't have to worry about the flux. It is always given. Okay, we don't have to worry about the flux, which is always given. Then I want us to come to this part. KF. Yes, guys, this is, I've said most, this is a form factor. This is the form factor, and the form factor is always equals to 1,1,1. But this is for a pure sine wave. So you know, most in theoretical questions or theoretical things, we are always dealing with a pure sine wave, even though in practical circumstances there is no such an alternator that that I know of that can produce a pure sine wave. Okay, so this is the form factor. You don't have to be told or given. You should know for a pure sine wave the form factor is 1 comma 11. Okay, then in the next session I am going to talk about these two short. In the next session that I'll be posting shortly, I'll be talking about the turns per phase and the pitch factor and the distribution factor.